It's a pleasure to introduce our next speaker, Professor Richard Schoen from the University of California at Irvine, who will speak on the Einstein constraint equations.
Well, it's a pleasure to speak at the 60th JDG conference. I've had a long association with JDG, and I think it's been a great thing for the subject. So it's good to have the conference and glad to be here. So what I decided to do today is to talk about a couple of recent results. So it's kind of a survey, but I'm going to take two sort of general recent results that I've been involved with and put them in a certain context for the constraint equations. And so I'm going to first just review the equations, and then I'm going to talk about the constraint manifold, which is the set of solutions of the constraint equations, which generally is an infinite dimensional manifold, or it might be singular in some. It's a kind of infinite dimensional moduli space, if you like. And then I'm going to talk about two kinds of constructions of solutions. One of them has to do with localization, that is making solutions trivial in large sets. And another one has to do with an extension problem, which is another sort of existence question that can be formulated for the constraint equations. And so let me begin by reviewing the Einstein equations. And I've written them here in n dimensions, although actually in the applications n will always be 3. So it's really the 3 plus 1 case that we'll be looking at. And so the Einstein equations describe the interaction of the gravitational field G with the matter fields, which are incorporated in the stress energy tensor T, which is on the right-hand side. An important case for us, in fact, most of the time I'll talk about the vacuum equations. And so if T is 0, that is, there are no matter fields, then the gravitational field is Ricci flat. Okay, and so those are called the vacuum Einstein equations. And remember that G is a Lorentz metric, so it'll have signature plus 3 and minus 3 pluses and 1 minus. Okay, and so solutions of the Einstein equations can be parametrized on initial data. So it's a hyperbolic system. And so the initial data is given on a hypersurface, and it'll always, in this talk, be three-dimensional. The specified initial data are the induced metric, it's the initial position, and the second fundamental form, which plays the role of the initial velocity. So second-order wave equation, so you expect to specify two initial conditions. And so an initial data set is a triple, then. It's a three-manifold with a Riemannian metric G that corresponds to M being space-like in the space-time, and then a symmetric 0-2 tensor P, which will be the second fundamental form in the space-time. Okay, and so a kind of unique feature of the Einstein equations, which is related to the fact that they're geometric, is that of the system of equations, there are n plus 1, n plus 2 over 2 equations. Some of them, namely n plus 1, so in 3 dimensions, 4 of the 10 Einstein equations are actually not dynamical. They're conditions that can be written entirely in terms of initial data. So they're what are called constraint equations. So they impose constraints on the G and the P, the given data. And the n plus 1 equations are a scalar equation which expresses the scalar curvature of the initial metric G in terms of a quadratic expression in the second fundamental form. And so that comes from the Gauss equations. Of course, it's a traced version of the Gauss equations. And the vector part of the constraint equations come from the Cauchy equations. So these come from the Gauss and Cauchy equations of differential geometry. And so the last n equations express the fact that a certain tensor is divergence-free, and the tensor is just algebraically related to the second fundamental form. So it's Pij minus the trace times the the metric. So those are the constraint equations. So in order to hope to have a solution, evolve a solution to the Einstein equations, the vacuum equations, these conditions have to be satisfied. And so it's very important to understand how to solve those equations and how to do it in a kind of flexible way. Okay, and that's sort of what the main focus of the talk is. So notice that this is a very underdetermined set of equations because they're only, in the three-dimensional case, there are only 4 equations for the pair of tensors. And so there are 4 equations for the GIJs and the PIJs, so 12 unknowns. So you expect to have a lot of flexibility in solving those. On the other hand, it's a nonlinear system of equations, so it's not always so clear to understand what the flexibility is. And so the initial value problem simply says, if you like, that solutions of the Einstein equations are parametrized uniquely on initial data. And so we don't worry about, we're not worrying here about large time behavior, but it's just a general theorem that if you take initial data satisfying the vacuum constraint equations, then there's a unique maximal globally hyperbolic spacetime which evolves from the data. Okay? So it doesn't address issues of long time behavior of the Einstein equations at all, but we can think of the constraint equations as parameterizing the globally hyperbolic solutions of the Einstein equations. Okay, and so in order to get a good problem, of course, we need to impose boundary conditions, and it's a little bit hard to impose finite boundary conditions for the Einstein equations, although there's certainly been many attempts to do so. For us, we're going to consider the two cases, namely the case when the initial manifold is compact. So in relativity, that's sometimes called the cosmological case. And so we have M, which is now a compact manifold, and we want to study solutions of the constraint equations on M. And then, in some ways, the compactness helps us because it makes the analysis easier. But on the other hand, there are certain things one can do in non-compact cases. The asymptotic sometimes give you more rigidity in non-compact cases. So the compact case isn't necessarily easier in general. Okay, and the other case I'm going to consider is the asymptotically flat case. And so this is, in relativity, called an isolated system. And it corresponds to data which, outside a compact set, looks like Euclidean space. And so I won't specify the exact fall-off, but what it means is if I remove from M a compact set, so the set that contains that topology, then the part near infinity looks like the exterior of a ball in Rn, and the metric falls off to the Euclidean metric at some rate, along with some derivatives, and the second fundamental form falls off to 0, okay, at some rate. And again, I'll talk a little bit more about the rates that are needed later. And so that's the second sort of boundary condition that I'm going to consider in the talk. And there are two basic examples in the asymptotically flat case. There's the Minkowski space and the Schwarzschild solution, Schwarzschild spacetime. So Minkowski is just Rn plus 1 with the flat Lorentz metric. And so if I take, say, the t = 0 slice, then it's just the Euclidean space Rn. And then the other one is the Schwarzschild spacetime. And I've written here initial data, the t = 0 initial data for the Schwarzschild spacetime. I've written it in conformally flat coordinates. So this is a conformal factor times the Euclidean metric, and it's defined on Rn minus the origin. And so this solution, when x is large, falls off to the Euclidean metric at a precise rate, namely of order 1 over r to the n minus 2, and it also blows up at the origin. So in fact, the origin is a second infinity for this solution. And so it's a vacuum solution. It satisfies, so p is 0 here, and the fact that this is a harmonic function is equivalent to the condition that the scalar curvature of G be 0. And so those are the constraint equations in this case. So it satisfies the vacuum constraint equation. In fact, it generates a static solution of the Einstein equations. And so it's a static black hole or the exterior of a static star in relativity. And you can think of it as being analogous to the exterior field for a point mass in Newtonian gravity. It plays an important role in many aspects of relativity. And so we can draw kind of a schematic picture of the Schwarzschild initial manifold. So if I think of x large being upward, then there's an asymptotically flat end at the top. And also it has a sphere of reflection, that red sphere there, which would be an S2, and that's a totally geodesic S2. And when you reflect across it, you get another copy of the metric is invariant. So so that's the geometry of Schwarzschild. Okay, and so again, in order to understand solutions of the Einstein equations, we need to understand the constraint equations. And so we can then look at the constraint equations as the zero set of a map. Namely, we can take, we'll call it capital Phi, the constraint map. And so we think of arbitrary Riemannian metrics and arbitrary symmetric 0-2 tensors, and then we can calculate this map, phi of GP. And so what it is just the quantities which are zero for the constraint equations to be satisfied. And so then the constraint manifold is simply the inverse image of zero under this map phi. And so we can ask, well, what's the structure of that manifold? And one of the key things that the key ideas here is, which in a certain sense kind of unifies the two recent results I want to survey here, is the idea of linearization stability. So this definition was given, I think, back in the 70s by particularly Jerry Marsden and collaborators of his. And the condition is that every infinitesimal deformation is actually tangent to an honest deformation, so a family of solutions. So one can ask, suppose we solve the linearized constraint equations, can we then integrate, can we then find a path of solutions of the nonlinear equations which is tangent to that? So that's called, if you can do that, it's called linearization stability. So given any solution, you can ask whether it's stable or not, linearization stable in this sense. And so let me just give a simple example. So if I just look at the quadratic map, x squared minus y squared on R2, and if I consider the set phi equals 0, then of course that just consists of the two lines through the origin, x equals plus and minus y. So this is phi equals 0. On the other hand, the differential of phi at the origin is 0. So in fact, every vector is in the satisfies the linearized equation. So d phi of anything is 0. And so on the other hand, there are only a couple of choices of vectors which are actually integrable. So there are conditions on very few of the solutions of the linearized equation actually can be integrated in an example like this. And so, of course, it's related to the fact that the differential is not surjective, right? So from the inverse function theorem, we expect that if the differential is surjective, then we would be able to, then the constraint manifold would locally be smooth, and we would be able to integrate infinitesimal deformations. Okay, and so in fact, the condition of linearization stability is actually equivalent to the constraint, the smoothness of the constraint manifold near a given point. So that essentially amounts to applying the inverse function theorem or the implicit function theorem in appropriate spaces. And so the question of integrating infinitesimal deformations is this idea comes up in many different moduli space problems. So in geometry, we always study solutions of equations. We want to understand whether or not the space of solutions is smooth. We always come across this question of being able to integrate infinitesimal deformations, or Jacobi fields, if you like, problems. And so it turns out for the constraint equations, there's a rather precise description of these solutions for which the differential is not surjective. And so what happens is that linearization stability fails only if and only if the spacetime has a killing vector field, so if it has a symmetry. So the symmetries of the spacetime give you linear solution to the linearized equation, which can't be integrated in general. That's the general idea. And actually, these same authors, Marsden and many collaborators, during the 70s gave a condition which characterizes the infinitesimal deformations that can be integrated. It's the vanishing of a certain quadratic tensor. So essentially, they showed that the singularities in the constraint manifold are of a quadratic nature. There's a precise quadratic term which vanishes. This is all in the compact case. So for compact initial data sets. So actually, this is a situation where the asymptotically flat case is actually better. In that Corvino and I showed about 10 years ago or so, actually in a JDG article, that linearization stability in fact does hold if you work in spaces in the asymptotically flat case where you impose decay. So the spaces involve some Sobolev spaces, but you require decay of the functions in the spaces. Then it turns out if you impose the natural decay in the asymptotically flat case, you don't run into this problem of singularities in the constraint manifold. So in that sense, it's simpler. Okay, and so this general idea of integrating infinitesimal deformations can be extended in a couple of interesting ways, and this kind of leads into the more recent work I want to discuss. Namely, one can ask, can you integrate infinitesimal deformations preserving support? In other words, suppose I take an infinitesimal deformation which is supported in some open set. Can I then integrate, I solve the nonlinear equations so that they are also supported in that open set? So that's a kind of localization for that. So in general, if you think of the constraint equations as an elliptic system, you would guess that you can't do that, right? If you try to solve a determined elliptic system, you will never be able to do that, basically. So, but on the other hand, remember that the constraint equations are a very underdetermined system. So in fact, it turns out in this case, you can do it again under the same conditions. Namely, if there are no space-time killing vector fields in the region omega, then you can actually localize the construction. So you can in fact solve the nonlinear equations with support in the same open set. And so in that way you can, in a certain sense, you can localize solutions of the Einstein equations, but only under this condition that you don't have space-time symmetries. And so you can also enlarge the idea a little bit by saying, well, the linearized constraint equations, although they're simpler than the nonlinear constraint equations, they're still not that easy to solve. And so it's still a linear system of equations. And so what you could try to do is remove the idea that the deformation you're looking for actually satisfies the linear system of equations. But instead, what you could try to do is you could try to specify a deformation which is only transverse to the constraint manifold. And then you could then project things. You could then construct approximate solutions and try to project into the constraint manifold. And so you can also generalize the idea in that sense, and then you can combine the two. You can say, suppose I take an infinitesimal deformation with some support and supported in some set omega, and suppose I do that and try to project in, then the question is, can I do it? And again, the answer is yes. There's a lot of, it turns out to be, there are rather robust methods to do that. Again, fixing the, even with fixed support, provided, again, that you don't have space-time symmetries in the open set. So, right, so we can then combine those ideas. Okay, so we can do a deformation, and we can project G tilde P tilde into the constraint manifold, and we can integrate in that form. So, and so what we can then do is we can take a solution to the constraint equations, and we can change it in some region without affecting the solution at other points. So in particular, you might think that, well, we could then localize solutions. So we could take our set to be the exterior of a ball or compact set, and we could make the solution trivial out there and keep it the same inside. Well, that turns out not to be possible because it would violate the positive energy theorem. And so there are certain things you can't do with the constraint equation, and it's related to the space-time symmetries, really. And so for example, I could say, suppose I take G and P in the Euclidean metric, and I deform them. So I write G tilde as G plus epsilon H, and P tilde is epsilon times K for epsilon small, and then I try to perturb that to be a solution to the constraints. Well, I can't do that keeping the support, keeping the compact support. However, I can do it if I allow things to be non-compactly supported. So if I allow these, so I can't do it with compact support, but if I allow things to be, if I allow some deformation near infinity, then it is possible to do that. So one has to introduce some non-trivial behavior at infinity, but one can control the behavior. So you could introduce something like a Schwarzschild metric at infinity, or Schwarzschild isn't quite general enough. You might have angular momentum, so you could introduce a Kerr solution. So it turns out the symmetry conditions that arise, or the obstructions, are directly related to the conserved quantities under the Einstein evolution. The energy, the linear momentum, and the angular momentum. There's also a center of mass term that comes in. And so you can sort of fully understand the extent to which you can do that sort of localization. So those are just some general ideas about the constraint equations. And I want to spend the last half of the talk talking about a couple of specific applications of those ideas. So actually, way back when Yao and I first did the positive mass theorem, there were some issues about the asymptotics that we assumed. The physicists claimed that the asymptotics were too special, we were assuming. So we actually managed to work out a very general theorem which fits right into the context that I'm talking about. Namely, we showed that you could take any solution, I say any solution for which the energy and the linear momentum are well defined, and you can approximate it, keeping it almost the same on a compact set. We didn't actually keep it the same there. But you could then sort of cut it off to Euclidean at infinity and then restore the constraint equations using a conformal deformation. So the G tilde is just a cutoff of the solution we started with. So I'm assuming here P is 0 in this construction. And then I can take G tilde, and then I can use conformal deformation to project it to the constraint manifold. Okay, and so in that way, you can approximate in a very natural norm, one in which the energy is continuous, you can approximate any solution which has good enough asymptotics to define the energy by one which near infinity is actually conformally flat. Okay, so it'll be the leading order a Schwarzschild metric near infinity. So that's an instance of this kind of idea. And actually, in that same paper I mentioned with Corvino, we generalized that to the space-time case. So there's also a way of doing that. Maybe I'm going to skip over this a little bit. So there's also a particular form that you can use in the space-time case to project back and do roughly the same construction. So you can again assume very good asymptotics in the solution just by doing a perturbation which is continuous in a natural norm in which the energy and linear momentum are continuous. I won't describe the norm carefully. Okay, and so, right. And so so that's an instance of it. But I want to talk about some more precise instances which involve actually the localization, so the idea of localizing solutions. And so again, the idea is that the constraints near infinity really are related to the conserved quantities, the energy, the linear momentum, and angular momentum. So since any of those can be achieved by any energy and linear momentum can be achieved by choosing an appropriate slice in the Schwarzschild spacetime, you could then ask, well, can we localize in the sense that can we take a general solution and replace it by one which is the same inside a compact set, but near infinity is exactly an appropriately chosen slice of Schwarzschild, or actually one has to use a Kerr. One has to introduce angular momentum here too to make this work. And in fact, it's correct. So we did that in that same paper, and there's also a treatment of that by Crucial and delay. Okay, and so that's an instance of that's the instance of the localized solving of the constraint equations, where we actually keep them exactly the same. So the solution we construct is exactly the same as we started with inside a compact set, and then near infinity we make it an exact Kerr, and it's smooth. Everything is it's not analytic, of course, but it's as smooth as you like. Okay, and so let me now talk about a more recent theorem involving localization. So generally, the Einstein equations have this feature that the initial data is constrained, so that we have the constraints, and those, of course, impose geometric conditions on the data. And so we can compare it to the wave equation. So if we look at the wave equation, of course, there are no constraints on the data, and we can approximate arbitrary data by compactly supported data usually in spaces that we work in. And so with the Einstein equations, we have this additional set of equations we have to solve. And so we can ask, well, so we can't localize solutions, so we can't expect to actually make the solutions trivial at infinity. But and in fact, there's a good linear analog of it. If we think of the Maxwell equations, we specify initial electric and magnetic fields, and let's assume B is 0. Then the energy, the electric field, satisfies the equation div E is 4 pi q, and so q is, say, compactly supported. It's a charge density, and in particular, there's a conserved quantity, namely the total charge of the system. And so again, in this situation, we can't approximate E and B by data which is compactly supported, because we have this. We can't approximate, at least in a norm. Well, we can't solve the equations in a norm where we keep the charge density the same or close on a compact set. And so, on the other hand, if you think about it, this equation div E equals 4 pi q. There's still a lot of flexibility in what asymptotic conditions you could expect for that. And so you can't make them compactly supported, but you can do lots of things with the asymptotics. And in fact, we're going to do something similar for the Einstein equations. And so we have this is these are the general conditions on the fall off for which the energy and the linear momentum are defined. So this means the metric falls off to the Euclidean metric. The 2 means along with 2 derivatives. So we can differentiate the fall off twice, and we get correspondingly stronger fall off. So this is x to the minus q, where q is bigger than this magic number, n minus 2 over 2. And then p falls off 1 order faster. So p is a derivative of g, so it should fall off faster than g to the Euclidean, faster than g does to the Euclidean metric. Okay, and so we want to understand what asymptotic forms we can assume for such data. And again, as I said, we can't make the data compactly supported. It's simply not possible to do that. And so actually, the positive energy theorem gives a more precise restriction on the data, which I've stated here. Namely, what it tells us is that if we consider solution of the constraint equations, And if we assume that it satisfies these slightly stronger, so these are the Schwarzschild type decay conditions. So the metric falls off like x to the 2 minus n to the Euclidean, and the second fundamental form like x to the 1 minus n. Then unless the data is trivial, if we take U to be the set, the open set consisting of those points where the Ricci curvature is non-zero. So the metric G might be flat in an open set, but there's some open set where the Ricci curvature is strictly non-zero. And then this set U, of course, the set U has to go off to infinity because otherwise the metric would be, we're in 3 dimensions, so it would be flat outside a compact set, and that's not possible. So in fact, more generally, you can argue that the set has a fixed cone angle in the sense that I've described there. Namely, not only does it go off to infinity, but it sort of has to, near infinity, if I cut it with a large sphere, the volume inside there has to be at least a fixed fraction of the total volume of the sphere. So the set of points where the solution is non-trivial has to actually go to infinity with some size. It has to subtend an angle at infinity. And so the proof of that's actually quite straightforward, except it uses a slightly different formula for the energy than is standard. Namely, there are lots of different ways of writing the ADM energy, and this is one of them. So the energy is actually the integral of a term involving the Ricci. So if you consider a large sphere and you look at the Ricci in the normal direction, and you integrate that over the sphere, and then you multiply by sigma and take the limit. It turns out that limit exists, and if you multiply by a suitable negative constant, it gives you exactly the energy. Okay? And so using that, it's very easy to prove the theorem. Namely, if so this is some positive constant, Cn. And so if the data is non-trivial, then the energy has to be positive. That's the positive energy theorem. And so in particular, if I take the sphere large enough, the integral there is bigger than, say, e over 2. If I take absolute values, it tells me e over 2 is less than this constant times sigma times the integral of the absolute value of the Ricci. And I'm assuming the fall off like x to the Euclidean plus order x to the 2 minus n. So the Ricci involves 2 derivatives. So it'll fall off like order r to the minus n. And then I have a sigma out front, so I get sigma to the 1 minus n times the volume. So in other words, the set U has to intersect the sphere in a set which makes up a fixed fraction of the volume. That's the consequence of that. So that's assuming the sort of standard decay conditions on the solution. So in particular, it tells us not only can't we localize solutions, we can't sort of make the support too small unless we give up the asymptotics, the asymptotic terms. And so in fact, let me state a theorem. So this is a theorem with Alessandro Carlato. And so we actually we showed that if you start with a solution which decays like x to the minus q, where q is between these two numbers, so it's less than or equal to n minus 2 and bigger than n minus 2 over 2, so the energy is well defined, then we showed that you can localize the solution in a cone. In other words, you can construct a new solution, which I'll call g hat. So again, so I've only stated the case here of zero scalar curvatures. That's the case when the second fundamental form is 0. But we also proved the theorem for the general constraint equations. I just won't mention it here because it's a little more technical. So the statement is that we can take our original solution and we can localize it in a cone. So I have draw a cone here. So we can draw a cone, and we can make the cone angle as small as we like. And we can leave our original solution alone there. So g hat is g there. And out here, g hat is delta, the Euclidean metric. Okay. And so everything, so sort of the non-trivial part of g is happening here. And the cone will be a cone that lies reasonably far out in the asymptotic region. Okay, so we can actually do the localization where the set that we localize in, so we perturb the metric only outside this cone, and we can make it exactly Euclidean outside the cone and leave it alone inside. Okay, and so there's this sort of general localization theorem. Now, there's a technical point here which is actually important. Namely, if I assume that Q is less than or equal to n minus 2 here, in the end, the G hat, we have to give up a little bit of decay. So if I assume that the decay was originally like the Schwarzschild decay, x to the 2 minus n, so in 3 dimension bx to the minus 1, then the G hat has slightly slower decay to Euclidean. So I have to take Q here to be less than n minus 2. I can't preserve the n minus 2 decay. And in fact, that's actually an essential feature of it. So if you could do that, then you would violate so these approximations preserve the energy. So I'm taking a general solution and I'm approximating it by one in a norm where the energy is continuous. So if I started with a solution which is roughly rotationally symmetric at infinity, then the energy would be evenly distributed in the various directions. And so if I look at the amount of energy in a small cone, then that's going to be a small fraction of the original energy. And so what happens is the extra energy has to concentrate in that transition region. And so for that reason, you cannot impose decay which is x to the 2 minus n, at least not with a fixed constant, because it would violate the conservation of energy in the construction. So it's a rather sharp theorem that tells you to what extent the Einstein equations could be localized. Actually, whenever I present this in physics conferences, the physicists never believe that solutions like this exist. When my kids were little, I used to tell them that gravity is not just a good idea, it's the law, right? But in a certain sense, this says it's not really the law. You can change it pretty flexibly. So on the other hand, of course, you can't really get rid of it entirely, but if you don't want to, if you want to only pay attention to things outside this very small cone, then in fact you can make it trivial. Okay, and so right. So I'm not going to go into the proof of the theorem, but you can view it again as a in this context of solving the constraint equations with fixed support. So in this case, it's quite a lot harder because the domains in which you're doing the perturbation are non-compact, and so in this case, understanding the behavior at infinity is a lot of technical work. But nonetheless, it is true, and also again, it's true for the general constraint equations as well, not just for the case when the second fundamental form is 0. Okay, and so I want to close just in the last 10 minutes or so by talking about a slightly different kind of solution of the constraint equation. So in a certain sense, if there's any coherent theme to the talk, it has to do with solving the constraint equations in a flexible way. So specifying specifying the kinds of behavior that you can obtain for them. And so this is a slightly different formulation of the existence question for the constraint equations. So and this idea was maybe introduced, maybe it appears earlier in the physics literature, but Robert Bartnik talked a lot about trying to solve the constraint equations where you specify some given compact set, and then you try to extend out. So it's the idea of extending data. And so what we can do is we can look at a compact region. So this is again a three-dimensional compact manifold with boundary. So I'll call the boundary sigma. And suppose I have data on that region. Say it satisfies the constraint equations. And then what we can do is look for extensions to asymptotically flat data. So we can try to take this finite region and put it into an asymptotically flat region, and so that the metric G extends and the second fundamental form P extends. So I'll call the extended data M G hat P hat. So these contain omega as a subdomain, and And then you can ask, is it possible to do that efficiently? In other words, if we take a given omega, can we do the extension in as efficient a way as possible? And the efficient way is one which minimizes the energy, so the ADM energy. And so this is a proposal that Bartnik made to define a quasi-local mass of the region. So the definition of the quasi-local mass is we consider a given finite region, and we look at all possible extensions to asymptotically flat data, and then we try to minimize the ADM energy. So it's a kind of capacity. It's the same kind of idea as in potential theory, where you look at the capacity of the Newtonian or logarithmic capacity. And so actually, there's a subtlety that occurs here in that you can't consider all possible extensions. You can only consider extensions where the boundary surface has some outer minimizing property. I mean, it turns out if you consider all extensions, you always get 0 as an answer, because you can do something like you can do something like make an extension here. Here's my region omega. And then you can do an extension which has, and you can put in a very small neck there. And so this you put in a very small horizon, and you can then make this metric, you can make the mass of that metric as small as you want. So it turns out you can always do that. You can always you can extend it in such a way that you produce this small horizon. And so you have to assume, so the way Bartnik formulated it is he assumed that there were no horizons that occur in the exterior data. But another way of formulating it, which maybe is a little more efficient, is that you look at extensions where the boundary surface is outer minimizing. So that means that any surrounding surface has larger area. Okay, so it's called outer area minimizing. So for example, a convex surface in R3 has that property, but in a picture like this, the surface sigma is here. This surface here surrounds it, but it's much, much smaller. Okay, so you want to look at extensions which are admissible. So admissible means that, so one definition of admissible, it's actually not clear what the right definition of admissible is, but one definition is that you require the boundary surface sigma to be outer minimizing. And then this is a variational problem. So you can look at all asymptotically flat extensions, and you can try to minimize the energy, and that's called the Bartnik mass. And so actually there's a very interesting lower bound on the Bartnik mass, which comes from a very beautiful theorem in the subject, which is called the Penrose inequality. It's proven by Schoen and Ilmanen. So in fact, the method was proposed by Robert Garrosh, who's a relativity guy. He proposed what's called the inverse mean curvature flow. So it's a geometric flow where you flow a surface with a speed given by 1 over the mean curvature. So you flow it, it's a sort of it's an expanding flow. And so Schoen and Ilmanen developed the rigorous existence theory for weak solutions of that flow. And it turns out under that flow, there's a certain mass quantity called the Hawking mass. And I've written it here for a surface. So I take any surface, then it turns out the Hawking mass under the flow is actually increasing. And so whatever extension you take, as long as the surface is outer minimizing, the eventual ADM mass is the limit of those Hawking masses, so it'll always be bigger than the one you started with. So there is a lower bound on the Bartnik mass, and the lower bound, of course, is achieved for the Schwarzschild case. In the Schwarzschild case, in fact, one of the motivations for the Hawking mass is that for the standard spheres in the Schwarzschild metric, these give you exactly the Schwarzschild mass. Okay? And so if you took Schwarzschild data, then this would be achieved. And so in general, there's an inequality there. But we don't know a lot about the Bartnik mass in general. But recently, Christos Montolides and I gave an interesting upper bound, which actually in a certain case, and I'll call it the black hole case, actually computes the Bartnik mass exactly. And it corresponds to, so it turns out, I didn't say it here, but the important bits of the boundary geometry that come up here for this extension problem, so the boundary data for the extension problem are the induced metric and the mean curvature. So it turns out that the boundary quantities that matter, so basically the scalar curvature of an extension has to do with the jump in the mean curvature across the boundary. And so you specify what matters is the induced metric and the mean curvature. And so notice, for example, the Hawking mass depends only on those two quantities. It depends on the mean curvature and it depends on the induced metric. And so, in the special case when h is 0 and the surface is called an apparent horizon, assuming it's outer minimizing, or a marginally outer trap surface sometimes. And so we actually showed that for any possible h equals 0 data, any possible metric on S2, so the sigma is always a 2-sphere in the black hole case, that actually one can construct an extension which comes arbitrarily close to the Hawking mass. So in other words, we showed that the lower bound of Huisken-Ilmanen in the limit is actually an equality. So in particular, if you take the infimum of the extensions, the masses of the extension, you get exactly the Hawking mass. So the Hawking mass in this case is just the square root of the area over 16 pi. So it depends only on the area of the surface. And so in fact, the method also produces a minimizing sequence for the Bartnik mass, which converges to a singular configuration. So it shows that the Bartnik mass is not always achieved. So when h is 0, it turns out it's not achieved, but we actually sort of explicitly construct a minimizing sequence for that in the construction. And again, I don't have time to go through it, but again, it's the idea of constructing special solutions of the equations. In this case, we want to do it in such a way that the mass is as small as possible. So we want to make a very efficient construction of solutions. And actually, you can ask to generalize whether this can be generalized to h non-zero. And in fact, it was recently extended by 4 authors, Cabrera, Cederbaum, McCormick, and Miao, to give an effective upper bound in the case of small constant h. So there is a kind of, it's not actually sharp in that case, but it reduces in the h equals 0 case to the theorem. And so it can be generalized. It probably can be generalized more as well. So let me just say, the other thing that we did in the paper is we characterized the possible geometries of the apparent horizons, or the black holes. So in fact, we showed that that the metrics on S2, which can arise as apparent horizons, which correspond in the p equals 0 case to stable minimal surfaces, they're precisely the metrics for which this operator has positive first eigenvalue. Okay, so in particular, any metric of positive Gauss curvature can be achieved, but you can also allow some negative Gauss curvature. So in this operator minus Laplacian is positive definite, and so it allows some negative curvature. In fact, we actually constructed examples where the integral of the negative part of the curvature can go to minus infinity, can go to infinity. It can be as large as you like. And so the horizons can be quite complicated geometrically, surfaces. The other interesting thing that this construction does is it gives examples for which the Bartnik mass is much, much smaller than other quasi-local masses, such as the Brown-York mass, which was generalized to by Mutau and Yao to the space-time setting. In fact, you can construct a sequence of examples where the Bartnik mass remains finite, but the Brown-York or Wang-Yao mass goes to infinity. So it's so in a precise sense, the Bartnik mass is sort of the smallest possible quasi-local mass. That, in fact, was one of the motivations for it. And so these examples show that, in fact, it can be made much, much smaller than the other, I think, most promising quasi-local mass, which is the Brown-York or Wang-Yao mass. Okay, and so I think that's all I have, so I'll stop there.